Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 1360, number of days between two dates. This problem challenges us to calculate the absolute difference in days between two given dates. We'll explore the most efficient way to solve it, step by step. Let's dive in. In this problem, you're given two dates as strings in the format YYYIMMDD, and the task is to write a function that calculates the number of days between these two dates. The input consists of two strings, date 1 and date 2, which represent valid dates. The format ensures that the year is a 4-digit number between 1900 and 2100, the month is a 2-digit number from 01 to 12, and the day is a 2-digit number that's valid for that particular month. The output should be an integer representing the absolute difference in days between these two dates. This means that regardless of which date is earlier, the result will always be a non-negative number. To make the problem more concrete, let's look at some examples. In the first example, we are given date 1 is June 29, 2019 and date 2 is June 30, 2019. The output for this case is 1 because the two dates are consecutive days, meaning there is exactly one day between them. In the second example, date 1 is January 15, 2020 and date 2 is December 31, 2019. The output here is 15, which represents the number of days between December 31, 2019, and January 15, 2020. This calculation accounts for the transition from one year to the next, ensuring that the days are counted accurately. Now, consider the third example. Here, date 1 is January 1, 1900, the earliest possible date in the range, and date 2 is December 31, 2100, the latest possible date. The output is 73414, which represents the total number of days between these two dates. This result includes leap years and considers the varying lengths of months, making it a comprehensive calculation. These examples highlight the importance of handling different scenarios, such as year transitions, leap years, and the wide range of dates within the problem's constraints. To solve this problem effectively, there are a few constraints and edge cases to keep in mind. First, both date 1 and date 2 will always be valid dates in the format YYYIMMDD, within the range of 1900 to 2100. The difference between the two dates will fit within a 32-bit signed integer, so you don't have to worry about overflow. The dates will never contain invalid values, like a 13th month or a non-existent day. You should also ensure that the function handles edge cases like identical dates, where the output should be 0, and leap years, where dates like February 29 need to be considered. Additionally, the order of the input dates should not affect the result. Whether date 1 is earlier or later than date 2, the output should always be correct. Finally, test cases with transitions between months of different lengths should also be handled appropriately to ensure accuracy in all scenarios. To solve the problem of calculating the number of days between two dates, we need to evaluate several approaches to determine the most efficient and reliable solution. First, we have the brute force approach. The idea here is straightforward: parse the input dates into their year, month, and day components, then iterate day by day to count the total number of days between them. While this method might seem intuitive, it becomes highly inefficient for large date ranges. Its time complexity grows linearly with the difference in days, making it impractical for scalability. Next, a more optimized option is the date library approach. By leveraging built-in libraries like Python's datetime or Java's localdate, we can handle parsing, leap years, and date arithmetic with minimal effort. These libraries allow us to directly compute the absolute difference between two date objects, resulting in a solution that is both concise and efficient. However, the downside is that this method relies on external libraries, which might not be permissible depending on the constraints of the problem or the environment in which the solution is implemented. Another approach to consider is the manual date difference calculation. This method involves implementing the logic to convert each date into the total number of days since a fixed reference point, such as January 1 of year 0. To do this, we need a helper function that calculates the total day count for a given date. This includes summing up the days from all completed years, accounting for leap years, and adding the days passed within the current year based on the month. Once we have the total day counts for both input dates, the absolute difference between them gives the desired result. This approach is efficient because the number of calculations remains constant, regardless of how far apart the dates are. However, it can be challenging to implement correctly due to the complexities of handling leap years and month boundaries. Even small errors in these calculations could lead to incorrect results, so careful attention to detail is required. For this problem, we selected the manual date difference calculation as our strategy. It offers independence from external libraries and guarantees constant time complexity, making it both scalable and efficient. The key insight here is that the Gregorian calendar operates on fixed rules for leap years and month lengths, which we can leverage to convert any date into a day count relative to a reference point, such as January 1st of year 0. Once dates are expressed as day counts, calculating the difference becomes a straightforward subtraction. A pivotal observation is the predictable pattern of leap years. They occur every 4 years, except for years divisible by 100 but not 400. This allows us to pre-compute or systematically account for leap years during our calculations. Additionally, the cumulative day counts for months can be stored in an array, eliminating the need for repetitive calculations. By reducing the problem to basic arithmetic operations on integers, this approach avoids the inefficiencies of iteration or the dependency on external tools. When comparing these approaches, the brute force method is clearly the least efficient, as it involves iterating through each day between the two dates. This makes it unsuitable for large date ranges. The date library approach is much simpler to implement and highly efficient, but it may not be permissible in scenarios where external libraries are restricted. The manual calculation approach, while slightly more complex to implement, provides a balance of efficiency and control. It requires careful handling of calendar rules but eliminates external dependencies and ensures accuracy. Ultimately, the manual calculation approach stands out as the optimal choice for solving this problem. It offers a robust solution that balances implementation complexity with performance, making it well suited for a wide range of scenarios and constraints. The problem we are tackling is LeetCode number 1360, where we need to calculate the absolute difference in days between two dates provided in the format YYYAMMDD. Since the Gregorian calendar includes complexities like leap years and varying month lengths, our solution must carefully account for these details. To begin, we start by parsing the input strings to extract the year, month, and day components. For example, given the date March 15, 2023, we extract year 2023, month 3, and day 15. Similarly, for December 25, 2020, we extract year 2020, month 12, and day 25. Once parsed, these components are converted from strings to integers for computation. After parsing, the next step is to normalize the dates. This simply means ensuring that the earlier date is always processed as the first one. If the first date is later than the second, we swap their values. For instance, if the first date is March 15, 2023 and the second is December 25, 2020, we swap them to maintain chronological order. Normalizing the dates simplifies our logic and ensures that all calculations move forward in time, reducing unnecessary complexity in subsequent steps. Now that the dates are normalized, we can enhance our solution using helper functions. The first helper function is is_leap_year, which determines if a given year is a leap year. A year qualifies as a leap year if it is divisible by 4, but not divisible by 100, unless it is also divisible by 400. For example, the year 2000 is a leap year since it meets the 400 divisibility rule, while 1900 is not because it fails this condition. Leap years are essential to handle February's varying length accurately. The second helper function, days_in_month, year, month, calculates the number of days in a specific month for a given year. This function uses the leap year logic to determine whether February has 28 or 29 days and returns the correct number of days for all other months. For instance, calling days_in_month, 2022, would return 29, while days_in_month, 2023, 2, would return 28. These helper functions modularize key pieces of our logic, making the solution more readable and easier to debug. The next major step is calculating the total number of days for each date relative to a fixed reference point, such as January 1st, 0000. This involves 3 substeps. First, we calculate the days contributed by all complete years before the given year. This is done by multiplying the number of years by 365 and adding the number of leap years that occurred during that time. Second, we calculate the days contributed by all complete months in the current year. summing the days for months 1 through month 1 using the days_in_month function. Finally, we add the remaining days within the current month. By summing these three components, we can determine the total number of days elapsed since the reference date for any given input date. Once we have the total days for both dates, the absolute difference between them gives us the number of days between the two dates. This approach avoids iterating through each day individually, making it highly efficient. When solving this problem, there are several key insights to consider. First, handling leap years accurately is critical due to their impact on February's length. The is_leap_year function ensures that our calculations for leap years are both correct and reusable. Second, our modularized design, which employs helper functions like is_leap_year and days_in_month, simplifies the solution by breaking the problem into smaller, manageable pieces. This design also makes the code easier to debug and maintain. Third, normalizing the dates to process them in ascending order eliminates the need for additional checks during calculations, streamlining the logic. Finally, the solution is efficient because we pre-compute the total days for years and months, avoiding the need to iterate through every day between the two dates. In terms of data structures, the solution relies on basic integer variables for year, month, and day components, alongside helper functions for encapsulating logic. No complex data structures, such as arrays or hash maps, are required, as the problem is solved using arithmetic and conditional logic alone. While the algorithm is robust, there are several edge cases we need to handle. First, we must ensure the solution works for dates within the same year, such as January 1, 2023 and February 1, 2023, where the difference is small. Second, leap year transitions must be verified when one date is in a leap year and the other is not. For example, February 29, 2020 to March 1, 2021. Third, we must handle transitions across centuries or millennia, such as December 31, 1999 to January 1, 2000. Fourth, when the two dates are identical, the output should correctly return 0 days. Finally, test cases where the first date is later than the second ensure that normalization works as intended. From a complexity standpoint, the solution is highly efficient. Since all operations are based on arithmetic and pre-computed rules, the time complexity is O(1). Similarly, the space complexity is O(1), because no additional data structures are used beyond the helper functions and integer variables. Let's walk through an example execution. Suppose the input dates are March 15, 2023 and December 25, 2020. First, we parse the dates, extracting year 1 equals 2023, month 1 equals 3, day 1 equals 15, and year 2 equals 2020, month 2 equals 12, day 2 equals 25. Next, we normalize the dates by swapping their order, so date 1 becomes December 25, 2020 and date 2 becomes March 15, 2023. Now, we compute the total number of days for each date relative to the reference date, January 1, 0000. For December 25, 2020, the total days amount to 737,790, and for March 15, 2023, the total days amount to 738,600. Finally, we calculate the absolute difference between these totals, abs. 738,600 to 737,790, which equals 810 days. This is the number of days between the two dates, and the final output for this example is 810 days. This solution leverages Python's datetime module to handle date parsing and calculations efficiently. First, the datetime.striptime method is used to convert the string inputs date1 and date2 into datetime objects. This parsing step ensures that the input strings are correctly interpreted as dates in the format YYYIMMDD. Once both dates are converted to datetime objects, the difference between them is computed using subtraction, which results in a time delta object. The .days attribute of the time delta object gives the difference in days. Since the problem requires the absolute difference, that abs function is applied to ensure the result is always non-negative. This concise approach ensures the solution is both accurate and easy to understand. The algorithm handles leap years, varying month lengths, and edge cases, like crossing year boundaries, seamlessly due to the robustness of the datetime module. This is the Java implementation for LeetCode problem number 1360, number of days between two dates. The logic mirrors the Python solution by using Java's java.time package for date manipulation. Key differences include the use of local date for parsing dates and chronounit.days. Between for calculating the difference in days. The result is returned as an absolute integer value. In this example, we're given two dates, January 15, 2020, and January 20, 2020. The function days between dates is called with these inputs. First, the datetime.strtime method is used to convert the input strings into datetime objects. This allows us to work with the dates programmatically. For the first date, January 15, 2020, it gets parsed into D1, and for the second date, January 20, 2020, it gets parsed into D2. Once we have these datetime objects, we calculate the difference in days by subtracting D1 from D2. This subtraction gives us a time delta object that represents 5 days. Since the difference is already positive, we take the absolute value, which remains 5. Finally, the function returns this value, and the output is 5, meaning there are 5 days between the two dates. Here, we have another example, but this time the dates span 2 different years. The input dates are December 31, 2019, and January 1, 2020. Similar to the previous example, the function days between dates starts by converting the input strings into datetime objects using datetime.strtime. The first date, December 31, 2019, is parsed into D1, and the second date, January 1, 2020, is parsed into D2. We then calculate the difference in days by subtracting D1 from D2. This subtraction results in a time delta object representing 1 day. Since the difference is already positive, the absolute value of 1 remains unchanged. The function then returns the result, which is 1. This means there is exactly 1 day between December 31, 2019, and January 1, 2020. Now let's look at an example where the dates are given in reverse order. The inputs are March 1, 2022, and February 25, 2022. Once again, the datetime.strtime method is used to parse the input strings into datetime objects. The first date, March 1, 2022, is converted into D1, and the second date, February 25, 2022, is converted into D2. When we subtract D1 from D2, the result is a time delta object representing -4 days, because the first date is later than the second date. To ensure the result is always positive, we take the absolute value of this difference, which gives us 4 days. The function then returns this value, indicating that there are 4 days between the two dates, regardless of their order. The final output for this example is 4. This demonstrates that the function correctly handles cases where the dates are provided in reverse order by always returning the absolute number of days between the two dates. When analyzing the time complexity of this solution, we start by looking at the parsing of the input dates. The datetime.strtime function processes each date string character by character to validate its format and extract components like the year, month, and day. Since the format of the input string is fixed, the parsing operation takes constant time, or O1. As there are 2 dates to parse, the total cost for parsing is O1 plus O1, which simplifies to O1. Next, the subtraction operation between the two datetime objects, performed as D2-D1, involves internal calculations to determine the difference in components like days, months, and years. This operation is also constant time, or O1. Finally, the calculation of the absolute value of the difference using that abs function is another constant time operation. Combining these, we see that all individual steps of the algorithm are constant time operations. Now that we've broken down the individual steps, the overall time complexity of the solution is O1, since each operation performs a fixed amount of work regardless of the specific input dates. Moving on to space complexity, we first consider the memory used to store the two datetime objects for date 1 and date 2. Each datetime object is a fixed-size object with fields for components like year, month, and day. Because the number of datetime objects created does not grow with the input size, the memory required for these objects is constant, or O1. Similarly, temporary variables like D1 and D2, which are used to store the parsed datetime objects, also consume a fixed amount of memory, contributing an additional O1 in space. Additionally, the input dates, which are passed as strings, occupy memory based on their length. However, since the format of the input is fixed as YYYAMMDD, the size of these strings is constant, meaning the space required to store the input is also O1. Importantly, this solution does not use any additional data structures or involve dynamic memory allocation, which keeps the overall space complexity constant. To provide some context, a naive approach to solving this problem might involve manually iterating through each year, month, and day between the two dates. This would require accounting for leap years and summing up the days in each intermediate month. For two dates that are n days apart, this naive approach would have a time complexity of O(n), as it iterates through all intermediate days. However, its space complexity would still be O(1), as it doesn't use additional memory. In contrast, our optimized solution leverages the datetime module, which provides efficient internal routines for date parsing and arithmetic. This eliminates the need to manually handle leap years or iterate through intermediate days. As a result, the time complexity is reduced to O(1), while the space complexity remains O(1). To summarize the best, average, and worst-case scenarios, the time complexity is O(1) in all cases because the algorithm processes a fixed amount of data independent of the input. Similarly, the space complexity remains constant as no additional memory is required. Mathematically, the big O notation reflects the asymptotic behavior of the algorithm as the input size grows. Since all operations in this solution, date parsing, subtraction, and absolute value calculation, are constant time, the overall time complexity is O(1). The fixed storage requirements ensure that the space complexity is also O(1), making this solution both efficient and highly scalable. When solving this problem, there are several common mistakes to watch out for. First, incorrectly parsing input dates can lead to runtime errors. For example, you might encounter invalid dates like February 30th, 2023 or inputs with non-standard separators. To handle this, validate inputs carefully or rely on built-in libraries that are robust in parsing. Another frequent mistake is ignoring leap years. It's easy to forget that some years, like 2000, are leap years, while others, like 1900, are not. This can lead to inaccuracies when calculating day differences manually. Additionally, the order of the dates matters. If you subtract an earlier date from a later one without taking the absolute difference, you could end up with negative results. Always use a function like abs to ensure correctness. Another inefficiency arises when using loops to count days incrementally. This brute force approach can become computationally expensive, especially for large date ranges. Instead, use mathematical calculations or libraries for faster solutions. Lastly, some solutions unnecessarily account for time zones or locale-specific formats, even though the problem explicitly uses the YYYIMMDD format and focuses only on day-level calculations. Keeping your implementation simple will save time and reduce complexity. This problem is designed to test several important skills in an interview setting. Recognizing patterns in date manipulation and understanding calendar nuances, such as leap years and varying month lengths, is a key aspect. Interviewers also look at how you approach the trade-offs between using libraries and manual implementations. Libraries like Python's datetime are quick and reliable, but solving the problem manually demonstrates a deeper understanding of the algorithmic process. Be prepared to discuss these trade-offs during an interview. Handling edge cases is another critical area. Scenarios like dates spanning centuries, leap years, or even invalid inputs are often used to test the robustness of your solution. Furthermore, understanding the time complexity of your approach is important. Library-based solutions generally run in constant time, O(1), while manual implementations may require O(n) time, especially if you're iterating over years or days. If you're interested in related problems, you might want to explore others like Problem 1154, which calculates the day of the year, or Problem 1118, which determines the number of days in a month, accounting for leap years. These problems can help you strengthen your skills in handling date and time calculations. There are multiple approaches you can take to solve this problem, each with its own advantages and trade-offs. A library-based approach, such as using Python's datetime or Java's java.time.localDate, is often the quickest and most reliable. These tools handle complexities like leap years and varying month lengths effortlessly. However, relying solely on libraries might not demonstrate your algorithmic problem-solving skills, which is something interviewers often value. On the other hand, a manual calculation approach involves breaking dates into years, months, and days, and then calculating the differences step by step. This method requires you to account for leap years and the varying lengths of months. While it shows a deeper understanding of the problem, it's prone to errors and less efficient than library-based solutions. Another alternative is to use the Julian day conversion method, where both dates are converted into Julian day numbers, and the difference gives you the number of days. This approach is efficient and avoids month or year specific complexities, but understanding the Julian day system might be unnecessary for many interview scenarios. Each method has its strengths, so choose the one that aligns with the context and requirements of the problem you're solving. Great work! We've successfully solved LeetCode problem number 1360, number of days between two dates. You now have a better understanding of date manipulation and edge case handling. If you enjoyed this walkthrough, be sure to like and subscribe for more coding tutorials. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!